Hi guys, this is geometry. We're gonna talk about lesson 7-3. Okay, in this lesson, we'll prove triangles similar. And we'll be able to use dilation and rigid motion to establish triangle symmetry theorems. Let's look at explore and reason. The measurements of the two triangles are shown. Triangle ABC and DEB are shown. And we got some lengths, all the lengths of the sides, and two angles given for each triangle. Are the triangles similar? How can we determine? Okay. All the sides are not equal in length, but how can we know if the triangles are similar? Well, in order for the triangles to be similar, by definition, they need to be able to be described using transformations, including non-rigid transformations, which is dilation. So basically, is there a factor, K, that describes the relationship or the proportion between the two triangles? So you want to find if all the lengths are proportional. So 32, the corresponding length for AB would be DE, right? So 32 over 40 must also be proportional to 24 over 30 and 35 over 45. Okay. So these are corresponding sides. So 32 over 40. So by theory, if they're similar, AB over DE must be corresponding to BC over EF must be proportional to CA over FD. Okay, and so you want to check if all of them are proportional. It's 32 over 40. What's 32 over 40? That's 4 over 5. If you divide both terms by 8. So that's 45, 4 over 5. What about BC over EF? 24 over 30. And then 36 over 45. If you divide both by 6, that's also 4 over 5. If you divide the last terms by 9, that's also 4 over 5. So all of them are proportional. Okay, and the angles are congruent. So the corresponding angles are congruent. A is corresponding to D, C is corresponding to F. And so 40 and 60, if the angles are the same and the lengths of the sides of the triangles are proportional to all the corresponding side lengths, then the triangles are similar. Let's write that down. Yes. The triangles have 3 pairs of congruent angles, and all corresponding sides are proportional. Because 36 over 45 is equal to 32 over 40, and that's equal to 24 over 30. There. So part B, would any triangle with 40 degrees and 60 degrees angles be similar to ABC? Think about that. So if we draw any triangles that has the same angles, so that's 40, and then that's 60, would it still be similar? Would this still be similar? 40, 60. Okay. If you think about it, by the triangle angle sum theorem, we know the other angle must also be the same, right? Any triangle with angles 40 and 60 will have a third angle 80. And then the sides will also be in proportion because we know that the angles, the opposite angles are proportional to the opposite sides. So let's type that in. Yes, by the triangle angle sum theorem, any triangle with angles 40 degrees and 60 degrees, third angle of 80 degrees. And the sides will be in, there you go. Okay, so in this lesson, we'll think about how we can use the angles and sides of the two triangles to determine whether they're similar. Okay. Let's look at example 1. Establish the angle-angle similarity theorem. We have similarity theorems for similar triangles. Okay, just like congruency theorems, they're going to be different, slightly different. So angle-angle similarity theorem. If we have two angles that are similar, how do we know if all triangles are going to be similar? Okay, if we have two congruent angles, can we prove that any two triangles are similar? We're not talking about congruency. They don't have to be exactly the same, but are they similar is the question that we're asking. Okay, let's look at this problem. If angle A is congruent to R and B is congruent to S, are the triangles similar? So to show the triangles are similar, we're going to determine whether there's a similarity transformation that maps ABC to RST. And first, we're going to determine the center of dilation, the scale factor that maps ABC to A prime, B prime, C prime, such that AB is equal to RS, like the length, right? So we're going to because AB is corresponding to RS, we're gonna dilate by a scale factor, let's say K times K, so that we get the same length as RS, okay? And then same for other sides, okay? Dilations preserve angle measure, so the angles are going to be the same. So S here, A here is now going to be corresponding to S. Wait, no. Yeah, A is going to be corresponding to R, B is going to correspond to S. And then we're gonna rotate so that we can rotate and translate so that we can map our transformation to the triangle RST. And using all the rigid motions and non-rigid motions and dilation, we can say that the triangles are similar. Okay, so see if you can try number 1. If angle A is congruent to R and C is congruent to C, how would you prove the triangles are similar? And now we have two other angles. So A congruent to R, C to T. A to R, C to T instead of B to T. It's gonna be the same process except what? You're gonna extend AC so that it maps to RT and it has the same length, right? And that's pretty much going to be the same way. Okay. Let's say you would determine the center of dilation, scale factor, K, that maps, whoops, over here, triangle ACB to image A prime C prime B prime. A prime C prime is equal to RT. Okay, and this is talking about the length. The dilation D KA has triangle ACB to A prime C prime B prime and triangle A prime C prime B prime congruent to triangle RTS by ASA theorem. So the triangles ACB and RTS are similar. Okay. Okay, here's the next page. Theorem 7-1 is angle-angle similarity theorem now. If two angles of one triangle are congruent to two triangles of another triangle, then the triangles are similar. Note that this is not a congruency statement. This is a similarity statement. We're not saying the triangles are congruent. We're saying they're similar, they're proportional. Okay. Let's look at example 2. Establish the side-side-side similarity theorem. We do have SSS theorem for the similarity as well. So if all the sides are proportional, we're not saying they're congruent now, we're saying they're proportional, then we have a similarity theorem. Why though? Okay, that means you can describe using the dilation, which is a transformation, to map one triangle to another triangle. So that means they're proportional and they have a similarity transformation and they are similar. Okay, let's look at try number 2. If DAF over GH is equal to EF over HJ, and angle F and J are congruent, is there a similarity transformation that maps triangle DEF to GHG? So DF, first, let's check if the lines are congruent, like they're corresponding. So DF here and EF, wait, DF and GJ. We're saying this over that, okay? DF and GJ is another way to see if they're all congruent, or if they are corresponding to each other. So EF would be these two corresponding to HJ. Okay, if these are proportional and the proportions are equal to each other, then and these angles are the same, then yes, there must be a similarity transformation that maps these two triangles, because if they're proportional and the angles are the same, what do we know about the third angle? You can dilate this with a scale factor of this proportion, EF over HJ, to map this to the same size as this other triangle. And then you know that once we do that, the triangles are going to be congruent, because once the sides are equal and then we have the angle that's equal, the triangles are congruent by SAS. So by definition of congruency, the other sides also needs to be the same. And there exists a rigid motion M that maps the triangle to another. Okay, so let's summarize that and write that down. So yes, when you dilate triangle DEF, better. Here, there's the triangle DEF, centered at vertex F with scale factor K is equal to EF over HJ to map triangle DEF to triangle D prime, E prime, F prime. When you do that, triangle DEF prime is congruent to triangle GHJ by SAS, triangle congruency theorem. And by the definition of congruency, there exists a rigid motion that maps triangle D prime, E prime, F prime to triangle GHJ. So the similarity transformation M of D transformations M and dilation map triangle DEF to triangle GHJ. So triangle DEF is similar to triangle GHJ. Yay. There you go. Okay. So here are more theorems. We got side-side-side similarity theorem and side angle side similarity theorem. So if we have sides that are proportional, not congruent, they're similar, the triangles are similar. And if we have two sides that have the same proportions and one angle that's congruent, then we have a similar similarity statement. Okay, example 3, verifies triangle similarity. Look at part A. Our triangles here similar. So first, determine whether the ratios are proportional. AB over DE is 2 over 3. BC over EF, when you simplify, is 2 over 3. And all the proportions are 2 over 3. So by SSS, the triangles are similar. What about part B? Are PQS and RQP similar? Well, see at first if the two pairs of given sides are congruent by ratio. Okay, so 27 over 18 is SQ over PQ. Okay, 27 over 18. When you simplify that, it's 3 over 2. PQ over RQ, they're corresponding. 18 over 12 is 3 over 2 as well. So they're proportional. Do we have the same angle? Well, they're proportional. And if they have the same angle, S or Q, then the triangles, the lengths of the sides that include Q are proportional. So you can use SAS. Okay. We already know that the angle is going to be congruent even though they don't have that notation because they're using the same letter Q. Okay. And it's from the same triangle. So this triangle is the red part. That triangle is the blue part here, but they share the same angle Q. Okay. So then we can say by SAS, they're the similar triangles. Okay, see if you can try by yourself. Can you explain how they're similar? And reason out as much as you can. Okay, so have you figured it out? Let's look at 3A. What are the triangles ADE, ABD? ADE, this one, and ABD, this one. Do they share any point? They share D, but they don't represent the same angle, right? So in triangle ABD, that is angle D. In triangle ADE, that's the angle D. Okay, and they're not equal. Okay, so we got 1.8, 1.8. That means this triangle is isosceles. Same for ABD. 2.4, 2.4. You have two sides that are equal. So that means the base angles are equal to each other. So what do we have? Two angles that are equal in the triangle, right? Is there any way we could prove that the sides are proportional? Well, 1 to 8 to 2 to 4 and 1 to 8 to the 4 is going to be the same. Is 2 to 4, we just need to check if 1.8 over 2.4 is equivalent. Is it equivalent to 2.4 over 3.2? Because those are the corresponding sides, right? Are they the same? Well, you gotta check. So do 1.8 divided by 2.4. You get 3 over 4. Okay, that's 3 over 4. What about 2.4 divided by 3.2? That's also 3 over 4. So they are proportional. All the sides, all the corresponding side lengths are proportional. So the triangles are similar by the SSS triangle similarity theorem. Yes. Okay, that's part A. Okay, what about part B? Is triangle ADE and BDC, are they similar? Let's see, where's ADE? ADE is the same triangle that we started with. BDC, BDC. Let's see, AD over BD, okay, corresponding sides, is it equal to DE over DC? Okay, so AD is 2.4, BD is 2.4, so equal to DE 1.8 over DC, which is 1.4. No, 2.4 over 2.4 is 1. That's 1. And 1.8 over 1.4 is 9 over 7. Okay, so no, they're not equal. The corresponding side lengths are proportional. Okay, so you need to check if the sides are proportional, or if you have 3 proportional sides already, or 2 angles that are equal and 1 proportional, 2 sides that are proportional and 1 angle that's equal, which is the included angle, then they're similar. Okay. Let's look at the next page, example 4. Finding lengths in similar triangles. So if we know the triangles are similar, could we figure out some information? Let's look at this problem. What's MN? Can we figure out MN if we know that triangles are similar? First, we need to prove that the triangles are similar. All vertical angles are congruent. So these two angles are the same. Okay. And then we know that these two sides are equal. Those two sides are equal, right? So there are isosceles triangles, which means this is also one. That's 75 as well, right? And the proportions are equal. So there are two corresponding sides that are proportional. And the included angle is congruent to each other. That means the triangles are similar by SAS, triangle similarity theorem. So this means similar, okay, or similarity. That's just a notation in math. So using the information of triangles being similar triangles can be dilated, right? Which means all the sides are proportional. So using this proportion, we can say mn over, so this is x that we're trying to get. X over 10 must be equal to 1 over 75. Okay, so that's our equation that you could set up. And if you multiply 10 on both sides, you get rid of this 10, and mn is equal to 10 over 75, which is simplified to 2 over 15. Okay, that's how you can figure out the lengths. So let's try number 4, A and B. So in example 4, if the measure of JL were 150 instead of 75, how would the value of MN be different? So if that's 150, what is your new answer? So instead of 75, that's going to be 150. So your proportion, your equation needs to be MN over, it's still going to be 10 because JK doesn't change, is equal to 1 over 150. Can you figure out MN? MN is 1 over 15 if you simplify. Okay. MN is half as long. Interesting, isn't it? What about part B? If the measure of JK was 20 instead of 10, how would the value of MN be different? So then you'll have the same equation, but MN is over 20 now. And that proportion must be equal to 1 over 75. We don't have both, but from example 4, you just change 10 to 20. And then your MN would be 4 over 15. It's twice as long, okay? Half as long. And now it's twice as long. Okay, let's look at example 5. Solve problems involving similar triangles. This is the application part. Avery puts up a radio antenna tower in his yard. Ella tells him that their city has a law limiting towers to 50 feet in height. How can Avery use the length of his shadow and the shadow of the tower to show that his tower is within the limit without directly measuring it? So you can consider the angle at which the sun hits Avery and the tower to be equal. And the triangle must be similar. Okay, because the sun is gonna stay the same and they're gonna be vertical. They're both gonna be vertical to the ground. So the angle that's made between the ground and the hypotenuse of the two triangles are going to be the same, and that's going to be vertical to the ground. So you have two angles that are the same, and so the triangles are similar. The small triangle here and the small triangle over there. You know, his shadow is going to be 5 feet, and then the shadow of the tower is 40 feet. Since the triangles are similar by AA similarity theorem, they're going to be corresponding sides are going to be proportional. So 5 to 40 is going to be the same as 6 to your height, ST. So then you can set up your proportions using the information you know, right? ST, so H is going to be ST, the side ST. ST going to be over 60, and that means 40 is going to be over 5, and they must be equal. And solving for that, multiply 6 on both sides, ST is equal to 48. Antenna tower is 48 feet high. Avery's tower is within the 50 feet limit, so it's okay. Okay, it's safe. So this is our last try. Try number 5. If the tower were 50 feet tall, how long would the shadow of the tower be? So now we know the tower is going to be 50 feet tall, and Avery's still going to be 6 feet tall, and the shadow is going to be 5 feet long. We want to know how long the shadow of this is going to be. So that's X. Okay, and they're still going to be similar triangles, so they're proportional. So you can say X over 5 is equal to 50 over 6. And multiplying 5 on both sides, you will be able to figure out X. What is it? 250 over 6 or 125 over 3 is going to be your answer. Or by a whole or the mixed number, your RT is going to be 41. Yeah, 41 and 2/3. Okay. The shadow of the tower would be 41 feet and 8 inches because 12 inches are 1 foot. Okay, so you could write either way. 41 and 2/3 feet, or 41 feet and 8 inches to be more exact. Okay, so let's summarize our lesson. We looked at some triangle similarity theorems. We have the angle-angle similarity, the AA similarity theorem. This is the abbreviation of angle-angle similarity. Side-side-side similarity theorem. Side-angle-side similarity theorem. Okay. Just make sure that the angles we're talking about here must be congruent, but the sides, we're talking about the proportions, not the congruency of the sides. Okay, so the sides do not have to be equal in length, but as long as they're proportional to each other, they're similar. We can use the similarity theorem. Okay, that's it. So that was our lesson 3 of topic 7, proving triangles similar. In our next lesson, in the next video, we'll learn about similarity in right triangles. How are they different? Okay. If you have any more questions about this lesson, feel free to ask Miss King in class. All right, guys, I'll see you in the next video. Bye.